So we are going to speak about, we're starting with dimensional methods, with dimensional analysis. What's the idea? Last week, if you remember, we have said a couple of times that one of the most important things when you are starting write down a mathematical model is to identify the important variables of the problem. That's probably the very first step that you are trying to do when you're writing down your mathematical model. But once you have identified the variables, the second step, which seems trivial, but it's extremely important, is to check if the dimension of your equations are correct. So if you have an equation which tells you that 4 apples are equal to 5 elephants, that's actually not good. It means that you are doing some mistake, because the left-hand side of your equation has some dimension, which is apples, and the right-hand side of your equation has another dimension, which is elephant. So possibly what's gonna missing there is some constant in front of the 4 apples, some k for apples, where k has dimension of elephants divided by apples, in such a way that left-hand side is equal to the right-hand side. Again, this observation seems trivial, but they are extremely important for assuring that everything is well posed. And I will show you in a moment that you can find even nice results for this basic analysis. So these observations are what are called, again, dimensional analysis. Let me give you then an example of how this works. The first example that I'm going to give you today is something which is called the blast wave problem, which is the problem of trying to understand what was the order of magnitude, what was the energy of an atomic explosion, an atomic bomb, just looking at the pictures of the blast wavefront of the explosion. Okay, this problem has been solved by a great British mathematician, which is Taylor, which is not the same Taylor of Taylor series. It's another Taylor. It's a very important applied mathematician. And actually, the story is very nice because the couple of papers regarding this model appeared in the late 40s. And it was a scandal because, because Taylor was able to provide an extremely good result for the energy released during the explosion of the atomic bomb. And this was top secret. So US thought that this result was top secret, and they were in panic when they said, oh, come on, there is a British mathematician that was able to publish this, this result in a while. So another brief parenthesis, actually, I spent few weeks working in Hiroshima a few years ago, and that's something incredible that I suggest everybody to do in the life, once in the life, because it's something very touching. That's the saddest story that I heard in my life. This girl, whose name was Sasaki-chan, that was invested by the blessed wave. She was outside, was not in Hiroshima Center, was outside with the brother, and she was invested by the wave, shocking wave, and at the beginning she was just kicked very far away from her brother. Her brother found her. She was probably a couple of years old. She found her. She was fine, but then she grew up. She was fine until 10 years, and then when she was 10, 11, they found that she had leukemia due to the radiation of the explosion. And the sad part of the story is that the brother told her that in order to express a wish, a desire, she should have done origamis of crane group. It's birth. 1,000 of origamis of cranes. And it seems that she was able to do just 700 in 1 year and a half, and she died. That's actually the heroine of peace for Japanese regarding this thing, the expression book. Close the parentheses. Then the calculation of Taylor. So the idea is that you have a large amount of energy which is going to be released in an extremely short amount of time. So let's do things as simple as possible. Let's suppose that this extremely small amount of time means that this huge amount of energy is released instantaneously, okay? And this energy is released in an extremely small space. Let's suppose that this energy is released in just 1 point. So you have 1 point, and instantaneously you have this energy E, which is very large, which is released. So then from this point, from the center, you have a shock wave, which is spreading outward. So basically, if you are taking pictures of this shock wave, what you will have is something that you observe like this at different times, right? So the shock wave is going outward. Why is going there? Because suppose that the pressure, which is inside this ball, very hot material, is it's larger and larger than the pressure of air outside. Of course, you have pressure of air outside, but if the pressure inside the ball is much larger than the pressure, then what you have is that this ball is going expanding, going toward outwards. So what Taylor assumed is that there is a relation between time, the front of the shock wave, R is the radius of this shock wave. The energy which is released in this process, and the density of air, the initial density of air. So Taylor assumed that there is this relation between these variables. And then what he did is dimensional analysis. So first thing, what's the dimension of energy? Tell me dimension of energy in terms of mass and length and time. So it's a mass, it's a force times a length, right? And the force is mass times an acceleration. So the acceleration is L times t minus 2. There is another L because it's force times length. So this is the dimension of an energy. Then what I have is the dimension of the density. Minus 2? Minus 3. Minus 3. It's a mass over a volume. So it's m times L minus 3. Then what I have? Then I have the dimension of time, which, guess what? Is time. And then I have the dimension of the radius of this shock wave, which is a length. Then what Taylor said is, okay, fantastic, I have all these things. Let me find a dimensionless variable, dimensional parameter that I can build out of this thing. So what he was doing was to find a parameter which was a combination of E, rho, T, and R in such a way that this parameter is dimensionless. Okay? You can play a bit with this parameter, so you have to multiply and divide E, rho, T, and R with the suitable combination. What we found is that the combination which is dimensionless, it's rho times r to the power 5 over e t squared. Okay? The dimension of these things here, this thing is dimensionless. So when we say that dimension is equal to 1, that's possibly an abuse of notation, but that's how you express that the variable is dimensionless. Indeed, you can substitute the dimension that you have for E, rho, T, and R and prove that this thing is dimensionless. Okay? So he proved that this quantity here is dimensionless. Fantastic. And then he applied the Pi theorem, which I was telling you before. So the Pi theorem, broadly speaking, the idea which is behind of the Pi theorem is that whenever you have a physical phenomenon, this is described by some mathematical equation, which is basically an expression, which is a relation between the different variables of your problem. It's like this G of T, R, E, and rho equal to 0. Okay? The Pi theorem tells you that this equation is equivalent to another equation which depends from other variables which you can build from your starting variables, but that are dimensionless. So basically, the Pi theorem tells you that this equation here that describes your model is equivalent to another equation, which I can call like f of, let me call pi 1 and pi 2. That's why it's called the Pi theorem, because the new dimensionless variables are indicated with pi. So your problem, which is described by this equation, is equivalent to the problem that is described by another equation whose variables are dimensionless variables built out from the initial variables, for the initial variables of your problem. Okay, so the pi 1, pi 2, whatever, are gonna be functions of T, R, E, and rho, but put in put in a way for being dimensionless, like in this case. So here I found the dimensionless expression of a combination of rho, R, E, and T. For this case, as far as I remember, this is the only combination that you have, which is dimensionless. So the Pi theorem tells you that this expression here, G of T, R, E, rho equal to 0, that I don't know, because I have no idea what is this expression which is describing these waves, these shock waves. Okay, this must be equivalent to this equation here.
Sorry.
Yeah.
Pi is always adimensional.
Pi is by definition dimensionless. Adimensional.
Sorry, the equation is rho to r to 5, or rho multiplied.
Rho times r to the power 5, so this is r to the power 5 divided by e t to the power 2. Okay? Now let me suppose that this is not a differential equation. Let me suppose that this is just some algebraic equation. Let me suppose that this is a transcendental equation, no derivatives inside. Okay? So what I can tell for sure is if there is any solution, this solution will be some constant. So let me call this constant with the great effort of fantasy C. So if this is a solution of this equation here, okay, this means that this must be true. Okay, that's like when you have, imagine that you have something like this. I know the solutions are x equal to 2 and x equal to minus 2. So I can write x equal to 2, which is a constant, or x equal to minus 2, which is another constant, right? So let me suppose that instead of having 2, I have a number. I know that the solution of this equation is some number c. So this means that this variable here, my pi, is going to be equal, one of the solutions of the equation is going to be pi equal to this quantity c. Okay? So without having any idea of what's the physics going on here inside this beast, I've been able to find at least what is the let's say mathematical behavior of the variable rho, r, e, and t, one with respect to each other. So what I can say is that I can rewrite this as r equal to c to the power 1 over 5 times e t squared over rho to the power 1 over 5. This is some numbers. Taylor supposed that this was equal to 1. It was just for simplicity. It was not interested really in this thing. In such a way that if I can observe a series of pictures, so imagine that I'm observing the picture at t equal 1 second, and the shock wave is like this one with some radius which is I don't know, let's say 10 meters. And then I observe that t equal to 2 seconds, another picture of the shock wave which is like that with a radius which is now, I don't know, 15 meters, and so forth and so on. If I'm observing this picture, this series of pictures, what I can do is to plot this function here, because rho, it's something that I know is density of the air. I can plot this thing, and what I can find is an estimate for the energy released in this process. Again, Taylor was extremely precise in finding this estimate. So let me give you a second example, which is going in the same direction, and then I will give a proof of the Pi theorem. Okay. So in the second example, there is me biking on a bicycle. Okay. If I'm biking, I'm very worried by the fact that I'm experiencing some resistance from the air. Okay. What's your experience? This resistance, which is the resistance that you experience from the air when you are biking, can you imagine from what this can depend? From the velocity. So I'm like that biking, so I discovered that I observed that this thing depends on velocity, wherever. What
Density.
else? Huh?
Density.
Surface? Density of what?
Density of air, I think.
Great. So density of air and surface. That's very good. The surface that I'm weak. The surface that I'm offering to the air should come into the problem, right? So let me write this as how did I write this in okay. A is going to be the area, is the surface that I'm okay. So what I will have is that the force due to the air resistance must be something which is a function of my velocity, the density of the air, and the surface which I'm with which I'm offering this resistance to the air. Which air is offering this resistance to the air? Actually, depends. So amazing. Now, I don't know what this function is. The only thing that I know is that I can write this as some constant k, and then it's going to be some, I'm postulating this, it's going to be some combination of the three variables that I suggest here. So it's going to be some rho to the power x times area to the power y times velocity to the power z. However, I know that if I'm taking now the dimensions of this thing, on the left-hand side I have a force. What's the dimension of a force? It's a mass times an acceleration, right? Times t minus 2. On the left-hand side I have k. I'm going to suppose that k is adimensional. Dimensionless. K times rho, so let me forget about k, times rho, which is a density, so mass per volume, to the power, to the power x. Then I have an area, which is L squared, again, to the power y. And finally, I have a velocity, speed, which is going to be L t minus 1 power z. Okay? So let's compare the left-hand side and the right-hand side. The left-hand side, mass is appearing with the power 1. On the right-hand side, I have mass which is appearing with the power x, which already tells me that x must be equal to 1. Okay?
Why x equal to 1?
Because on the left-hand side, I have mass power 1. Eh? Just a second, we're rabbit 12. It's the next one. Okay, so x must be equal to 1. Let me already put here x equal to 1. Okay, now let's calculate what happens for L. L on the left hand side has power which is again 1. On the right hand side, I have now power minus 3 from here, and then I have plus power 2y from here, and then I have power z. And finally, I have t. T on the left hand side has power minus 2, and on the right hand side, is correct? Yes. On the right hand side, it has power minus z from here, which basically means that z must be equal to 2. If I take z equal to 2 from the second equation, what I get is 1 plus 3 is 4, 4 minus 2 is 2, equal to 2y, which tells me y equal to 1. Okay? So x equal to 1, y equal to 1, z equal to 2. This means basically that the resistance that is opposing air when I'm biting in some direction is going to be proportional. Remember that there is the factor k in front of my equation. It's going to be proportional to what? Rho to the power x. So rho to the power 1. A to the power y, which is again equal to 1, and v to the power z, which is equal to 2. So the air resistance is not going like velocity, it's actually going like velocity to the power 2, velocity squared. So again, this is a result that without knowing anything about the physics and blah, 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 just checking the dimensions of the problem that I'm trying to solve, well, it's a result that I'm able to find, which is already a nice result, which is already something which tells you some nice information. Okay, now let's then, any problem? Any problem so far? No, I'm assuming the answer is no. For the rest of the...
Sir,
okay.
I'm sorry. What is car? I don't understand the role of the car in this equation. Because in the...
K, you mean?
Yes, yes.
Okay, this K is just some constant. I don't know anything about that K. Since I don't know this law which is relating the force of the resistance of the air to density, area, and velocity, what I'm assuming is that there is some parameter K, which is dimensionless, to be added to my problem. So I'm assuming that I'm sure that the resistance of the air is gonna be a function only of rho, A, and V, and then if there is any number in front of this rho, A, this combination of rho, A, and V, well, it's gonna be in this K. I don't care what's the number. The only thing that I would like to understand is what's the relation of the force of the resistance of the air between the force, the resistance of the air, and rho, A, and V. And what I discovered is this expression here. So the resistance of the air is gonna be proportional to the density of the air, proportional to the surface that I'm offering to the air, and proportional to the square of the velocity, and not just the velocity. Okay? K, forget about it, just number.
Oh, okay. Thank you.
All right. Now, for the rest of the class of today, we're gonna prove this Pi theorem, this Buckingham's code. Buckingham. Pi theorem. Buckingham is the guy that proved the theorem. And again, the theorem is called Pi theorem because, well, historically, traditionally, you are calling these dimensionless variables with pi, right? No, it's not a very deep.
This it's used for protecting. Maybe sometimes we need to protect some protection. Maybe airplane should be protect a small model, and when this model is very nice, we should be use this method for protecting
the resistance, for studying the resistance of the air, you mean?
Yes.
Yeah, actually, this is a kind of model which is used in many problems of motion through a fluid, because it's very basic model. It's not even a model because I'm just presenting what should be the shape of the force. Okay, what should be the dependence of the force on these other parameters. It's some kind of very naive assumption, but works in a lot of situations. So apart from more complicated stuff, probably what you would have is some geometrical. So the K is going to be related to some geometrical assumption on the system that's moving through the fluid, for example. However, Buckingham's Pi theorem. So let me consider, by the way, parentheses, even if you don't find the book in the library, I will put soon my handwritten notes on our Teams page. I hope that you're able to understand it. Are they fine? Huh? Are they okay? Okay, great. Huh? Yeah, exactly. Actually, I'm renumbering now in terms of weeks, so this is gonna be 2-1. I'm gonna put these things, and basically you find all the materials on these notes. Again, since this is my first year, these are handwritten notes, and I don't really have the time to transpose these in LaTeX. I'm sorry for that. So Buckingham's Pi theorem. Let me consider m variables, m quantities. So I have some q1, q2, qm. And these quantities, these variables are dimensionful. They have dimensions. Okay. Let me suppose that, for example, the dimension of the ith quantity, the quantity number I, is equal to L1 to the power A1 with I, L2 to the power A2 with I, blah blah blah, Ln with the power A n I. Is this correct? Yes, this is correct. Okay, fantastic. Let me comment a second this thing. So I'm assuming that all the variables Qi's, Qi is wherever, a variable here inside, Q1, Q2, Q45, or wherever it is, okay? So I'm assuming that all these Qi's are dimensionful. So I can find what's the dimension of the Qi, and the dimension of Qi, I know where it is. It's this combination of L1, L2, Ln to the powers A1, A2, and An. So imagine, for example, that Qi is a force. This means that this would be this kind of combination where L1 is the mass, L2 is length, L3 is a time. And where this power here, A1I, well, this I runs for, of course, between 1 and m. So this, for example, suppose that f is my q1, then I know that a11 is going to be equal to the power of m, so it's going to be equal to 1. A21 is going to be equal to the power of n, which is again equal to 1, and A31, which is this guy here, is going to be equal to the power of t, which is minus t. Okay, and I'm doing this for all the variables that I have in the problem. Again, I have m dimensionful variables on the problem, and each dimensionful variable can be written in this way. Note that the number n of fundamental dimension is less than m. Okay, so for example, here I have 1, 2, 3 fundamental dimensions: mass, length, and time. This is equivalent of this number n. I want this number n to be smaller than the number of independent variables that I have in the problem. So this means that I don't have only f, but I have other stuff. Whatever. Now, let me define the matrix A, which is the matrix of the exponents of the Q of the dimension of the QIs. So it's the matrix of these exponents here. So since I have this set of exponents for every for each variable, I will have, of course, I can of course build up a matrix of these exponents. So here I will have A11, A12, blah blah blah, A1M, A21, A22, blah blah blah, A2M, until I reach AN1, AN2, blah blah blah, ANM. Right, so this. Yes. Now, suppose that R is the rank of the matrix A. What does it mean? Do you remember what is the rank of a matrix? Huh? The number of independent rows or columns. Okay? So this basically means that this matrix A has, which has rank equal to R, has R independent columns or R independent rows. Then the idea of the Pi theorem, of the Buckingham theorem, is that there exists, what I want to prove is that there exists M minus R independent, dimensionless quantities that I will call pi1, pi2, blah blah blah, pi m minus r, which can be formed, which can be constructed from q1, q2, and qm, and such that the physical law, which is some f of q1, q2, qm equal to 0, is equivalent to f of pi1, pi2, pi m minus r equal to 0. Should I repeat? I will repeat. So again, the idea is I'm starting with m independent variables, which are dimensionful. I based out the matrix of the exponent of dimensions of each of these variable. This matrix will have a certain rank, which is this rank R. Then what I would like to prove is that there exists m minus r independent and dimensionless quantities, pi1, pi2, pi m minus r, that I can build from q1, q2, qm, and such that I can express the physical law, which is given by this equation, in this other way. So with this other equation, where the number of variables, of course, m minus r is less than m. So what I'm doing is to save a lot of efforts, because I have less variables than in the first problem. So let's prove. Let's start by proof that I can find the m minus r independent dimensionless parameter, and then I will prove the equivalence between these two equations. So let me start by noting that this matrix here, as you probably remember, can be seen as the matrix of the coefficients of a homogeneous linear system of m variables. So basically this is exactly the matrix that you can write down from my system a11x1 plus a12x2 plus blah 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 a1mxm equal to 0, and you can do the same for the other ones. Okay. If you look to the matrix of the coefficients of this linear system, well, that's exactly my matrix, the matrix that I call here A. Now, there is a fundamental theorem in linear algebra which tells me that if this matrix has rank R, this means that there exists m minus r independent solutions of the system here. Okay, so the fact that my matrix A has rank R tells me that this system has exactly m minus r independent solutions. Now, let me suppose that the generic variable pi, which remember is a dimensionless variable, so let me suppose that the generic pi can be written as the following combination of q1 of the variables qi's. So it's q1 to some power alpha 1 plus times q2 to some power alpha 2. Note that alpha 1, alpha 2 for the moment are unknown, times qm to the power alpha m. Okay, so basically this means that I can substitute to q1, q2, qm, and so forth and so on. I can calculate the dimension of this thing on the left hand side and on the right hand side. On the left hand side, I have this, which is equal to 1. On the right hand side, I will have the dimension of q1 to the power alpha 1, the dimension of q2, the dimension of q2 to the power alpha 2, so forth and so on, until the dimension of qm to the power alpha m. But I know what are these things here, because these are exactly the these expressions that I know by hypothesis. So I know that QIs can be written in this way. So what I have to do is just to substitute this expression here in all these quantities. So what I will have is L1 A11, L2 A21, blah blah blah, Ln AN1 to the power alpha 1. The same for the second term and the third term till I reach L1 to the power A1M. Just a second. Just a second, it's not working the tablet. Please. So what? Okay. So this is L1. Can you see the screen there at home?
Yes.
Yes.
Okay, great. Okay,
Yes.
thank you. So what is here? A1M Ln ANM to the power alpha M. So basically, what I can do now is to build some, well, here I will have some L1 to the power A11 times alpha 1 plus other terms which are coming from the terms which are here in the middle until I arrive to plus A1M to the power times alpha M times L2 for a similar expression times L3, L4, L5 until I arrive to Ln with a similar expression again. Just a second. So basically, what I will have now, note, on the left-hand side, I have just one. Okay, I can write this one as L1 to the power 0 times L2 to the power 0 times Ln to the power 0, right? So basically, what this expression is telling me is that all these powers must be equal to 0. So A11 alpha 1 plus A12 alpha 2 plus A1M alpha M equal to 0. Then I have A21 alpha 1 plus A22 alpha 2 plus blah 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 A2M alpha M equal to 0. All down till I reach ANM alpha 1, no, M alpha M, sorry, plus blah 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 blah, N1, sorry, AN1, ANM alpha M, this is a 1. AN1 alpha 1, ANM alpha M equal to 0. So I have this system. Now this system, well, that's exactly this system here, where alpha 1, alpha 2, and alpha m are taking the roles of x1, x2, and xn. And remember that this system here is basically the system whose matrix of coefficients is the matrix A, my starting matrix. So this means, for what we have said before, that this system has m minus r independent solutions, which are for alpha 1, alpha 2, alpha m. So I can find m minus r independent tuple of vectors of alphas which are independent. So m minus r vectors of alphas which are independent. Again, this begins from the fact that this is the linear system which corresponds to the matrix A, which is a matrix of rank R. Okay? Now, each of these independent solution, so each of these vector alpha 1, alpha 2, alpha m is going to correspond to a single pi. So this means that each of the m minus r independent solutions will correspond to one of the new dimensionless variable pi. So this is going to be, these pi's are going to be dimensionless by construction. Because you remember here, I construct this system here from the hypothesis that this is the most generic pi that I can build out by Q1, Q2, and Qm. This is dimensionless by hypothesis. So what I'm trying to find is the independent pi's. So the combination of alphas here, which is gonna give me independent dimensional variables, independent pi's. And that's actually what I have from studying this linear system and finding the solutions of this linear system.
But the generic pi is not dimensionless.
The generic pi is dimensionless, adimensionale. It's written here. This is the, by hypothesis, I'm considering this dimensionless.
So also the last one.
This part, you mean, the right hand side?
The pi j.
These ones are going to be all them dimensionless. So this pi j are just this pi with a certain alphas. Okay, so basically, again, you find if you impose pi to be, the generic pi to be dimensionless, this means that I'm looking for the combination of q's, of qi's, such that I can find some dimensionless parameter. I can have different combinations, which is dimensionless, right? This depends on the alphas. For example, I can have some combination of q1 squared times q2 to the cube, which is dimensionless. Very good. This will correspond to alpha 1 equal to 2, alpha 2 equal to 3, and nothing else. Then I will have some other combination. Okay, fantastic. What I want to do is to find all the possible independent combination. And all the possible independent combination can be found solving this linear system. So this linear system is going to give you the independent vectors, m vectors of alpha 1, alpha 2, alpha m. All the independent vectors alpha 1, alpha 2, alpha m. And all of them each of them will correspond to one dimensionless pi. Now I put this j just to say that there are going to be j between 1 and m minus r, because it's going to be m minus r independent dimensionless variables. Okay, so this is the first part of the theorem. So this proves you that if I'm starting with m of Madrid independent dimensionful parameters, then I can find out some m minus r independent dimensionless parameters, which are combination of the qi's, of the starting qi's. Okay. Now the second part of the proof imply that we have to show that the physical law f of q1, q2, qm equal to 0 is equivalent to some other law that I want to write in terms of pi's. So this law is some f is a whatever function of pi1, pi2, pi m minus r equal to 0. So this would prove me that, this would show me that if I'm starting with a problem which has, I don't know, 100 of parameters, I will be able to find a small number or a smaller number of parameters, let's say even 99, but 99 is less than 100, with which I can express the problem. So I can save some variables in the problem, which means basically that I'm doing less work when I'm trying to solve the problem. So in order to prove this thing, we will not prove this part of the theorem with the generic m and r, because otherwise it's a mess. So I'm gonna use m equal to 4, n equal to 2, and r equal to 2. Guys, I'm continuing without pause, in such a way that well, we will finish this theorem, and I don't know if there is any time for something else, but thanks. I will try to finish before the 4 p.m. So we will prove the theorem with m equal to 4, n equal to 2, and r equal to 2, which you can generalize it, but the generalization is extremely complicated, cumbersome, with a lot of calculation and a lot of indices. Since I'm not interested in confusing your ideas more than what they already are, probably, let's do this thing with this simple version. So this basically means that my physical law is some f of q1, q2, q3, q4 equal to 0. Then n equal to 2 means that these q1, q2, q3, and q4 are expressed in terms of just two fundamental dimensions. So each of the qi's, I run from 1 to 4. So for each I have the dimension of qi is equal to L1 to the power A1 I times L2 to the power A2 I. so that I can write my the matrix of the coefficients as A11, A21, A12, A22, A13, A14, A23, A24. By hypothesis, the rank of the matrix is 2. So the fact that I have a rank equal to 2 basically means that I have just 2 independent columns in this matrix. Now, the generic pi, what's the generic pi? The generic pi is going to be some q1 to the power alpha 1 times q2 to the power alpha 2, q3 alpha 3, q4 alpha 4. So remember that if I can express pi in this way, this means that if I'm taking the dimensions of pi is 1. The dimension of the right-hand side is going to be the product of these factors. Okay? So basically this means that taking the dimension on the left-hand side and the right-hand side and equating the exponent of the corresponding L on the left-hand side and the right-hand side, I will find this linear system. Oops, this is A. So again, this linear system, I found this linear system as I found the linear system here. What I've done is to substitute this is equal to 1, and on the right hand side I have L1, A11, L2, A21 to the power alpha 1 times L1, A12, L2, A22 to the power alpha 2, and so forth and so on for Q3 and Q4. And then what I do is to take all the powers of L1, so it's A11 times alpha 1 plus A12 times alpha 2 plus the other ones for 3 and 4, and this is going to be equal to 0. That's the first equation. And then I take all the powers of L2. So I have A21 times alpha 1 plus A22 times alpha 2, and so forth and so on, again equal to 0. And this is giving me the second equation. Remember that this is equal to 0 because on the left hand side, this 1 corresponds to L1 to the power 0 times L2 to the power 0. That's why I have these zeros here. All right, so now I have this linear system. Now, since by assumption the rank of this matrix, we say that is equal to 2, then I can assume, I'm assuming for simplicity, that the independent columns are the first one. So this is an independent column and this is another independent column. And the other two columns can be expressed in function of these two. So this means that I can write the column A13, A23 as a linear combination of the first two columns. And similarly, I can write the column A14, A24 as another linear combination of the first two columns. Here, C, D, E, and G are some constant coefficients. But then, this means that I can use this expression of these columns A13, A23, and A1424 to rewrite this, sorry, not this. To write this linear system. So what I have to do is to substitute the column A14, A24, and to substitute the column A13, A23, using the expression that I found. What you will get is this combination A1 plus C, sorry, alpha 1 plus C alpha 3 plus E alpha 4 times A11, A21 plus alpha 2 plus D alpha 3 plus G alpha 4 times A12, A22 equal to 0, 0. So basically this is exactly the same linear system that we have here if we substitute these two expressions here. So I take these two expressions and substitute in the linear system. And what I get is this other linear system. Now, note that we say that the two vectors A11, A21 and A12, A22 are linearly independent. You remember, because the rank of the matrix is 2, and I choose the first two columns to be linearly independent. Now, in order for if these vectors are linearly independent, and I know that this combination of these two vectors is equal to the 0 vector, then what can I say on these coefficients here?
They are 0.
They are 0. They are 0. Alpha 1 plus C alpha 3 plus E alpha 4 equal to 0, and what's the second? Alpha 2 plus alpha 3. No, there's something missing there. There's a D missing. Yes. Plus D alpha 3 plus G alpha 4 equal to 0. If I'm solving this, suppose that I'm solving with respect to, in terms of alpha 3 and alpha 4, I get this alpha 3 minus C minus D 1 and 0, alpha 4 minus A minus G 0 and 1. So basically these are this vector here and this vector here are the two independent solutions which correspond to the two independent pi's. So this corresponds to two independent dimensionless parameter pi. So I will call pi 1 So remember that the pi's are combination of Q1, Q2, Q3, and Q4. So this is the combination Q1 to the power minus C, Q2 to the power minus D, Q3 to the power 1, and Q4 to the power 0. So let me cancel Q4. Let's do the same for the second pi 2. Pi 2 is again Q1, Q2, Q3, Q4 to which power? Q1 is to the power minus E, Q2 is to the power minus G, Q3 is to the power 0, Q4 is to the power 1. So Q3 to the power 0 again is equal to 1, so let me cancel it. Let me write Q4 1 here. So what I found are this expression pi 1 and pi 2 of two independent dimensionless parameters expressed in terms of Qi's. Note also another thing that this means also that I can express Q3 and Q4 in terms of what? In terms of Q1, Q2, and pi 1. And the second one in terms of Q1, Q2, and pi 2. Such a way that you remember my physical law, the law that was ruling my mathematical model was f of Q1, Q2, Q3, and Q4 equal to 0, which can also be written as f of Q1, Q2, Q3 is a function of Q1, Q2, and pi 1, and Q4 is a function of Q1, Q2, and pi 2. So this basically means that I can find from here some other function f tilde, which is a function of Q1, Q2, pi 1, and pi 2, which is equivalent to this, but that now are expressed in terms of these new variables, in terms of Q1, Q2, pi 1, and pi 2. Okay? That's not the end of the story, because I still have Q1 and Q2. So the next step is to find a way to get rid, to forget about Q1 and Q2. And what I can do is to consider the fact that physically any quantity can always be rescaled. So what I want to do is to rescale, oh no. What I want to do is to rescale Q1 and Q2 to some Q bar 1 and Q bar 2 in such a way that Q bar 1 and Q bar 2 are equal to 1. So the rescaling is going to be something like this: lambda 1 power A11, lambda 2 power A21 Q1, lambda 1 to the power A12, lambda 2 to the power A22 Q2. So note that lambda 1 and lambda 2 have to be chosen in such a way that with powers A11, A21, A12, and A22, I can define this new Q bar 1 and Q bar 2. Broadly speaking, what's the essence of this transformation? That's actually what you do when you are rescaling, for example, kilograms to grams. That's actually exactly the same thing. It's a rescaling of this kind. Because what I want to arrive to is some quantity Q bar, which I can safely say to be equal to 1. or equal to some, no, equal to 1. Yeah. So if I want to obtain this thing, if I want q bar 1 and q bar 2 to be equal to 1, let's see how can I satisfy this linear system. Let me take the log, the logarithmic natural log on both sides, left hand side and right hand side. The log of 1 is 0. On the right hand side, I will have log of lambda 1 a11 lambda 2 a21 times q1. The product of the log is equal to what? The log of the product, sorry, the log of the product is equal to sum. And the log of a power? Exactly. So this expression here is a11 log lambda 1 plus a21 log lambda 2 plus log q1. The same happens for the other one. So this is log of 1 is equal to 0. And on the right hand side, I will have log a12 log lambda 1 plus a22 log lambda 2 plus log q2.
Okay, the reason that log before a to a1 to.
No, this is cancelled, sorry. This was a mistake. Okay? Now this is again a linear system which is inhomogeneous because you have the terms log q1 and log q2. But it's a linear system in the variables log lambda 1 and log lambda 2. Okay? And this linear system has the corresponding matrix of the coefficients is a11, a21, a12, a22. But the great surprise, no, but because basically this is just the matrix of the coefficient of these two equations. So basically you can get these equations if I'm considering, I have to multiply on the other side. Sorry, this is 1, 2, 2, 1, lambda log 1. Sorry, I messed up. That's, no, sorry. Okay. So it's 1 times log lambda 1 and 1 times log lambda 2. Exactly. And this is 2 times exactly. All right. And this is going to be minus log q1 and log q2. So basically, this one is the matrix of the coefficients of this linear system. But the interesting thing here is that we know, always by hypothesis, that these two vectors are independent. These are always the same vectors of the same of the beginning of the problem. So that's the two vectors that are supposed to be independent here at this stage of the proof. Now, since these two vectors are independent, this means that, again, this is an important and fundamental theorem of linear algebra. This means that this linear system has a solution. There's just one solution. So the solution existed is just one. What does it mean? It means that I'm surely able to find a lambda 1 and a lambda 2 such that this system is true, is fulfilled. These two equations are fulfilled. Okay? This means that I'm always able to find a lambda 1 and a lambda 2 in such a way that q bar 1 and q bar 2 are both equal to 1. Now, since a physical law does not change if I'm rescaling the quantities, this means that if this physical law is true, then also this other is going to be true. Oops, bar 1, q bar 2, pi 1, pi 2 equal to 0. Then, since I can do the rescaling in such a way that q bar 1 and q bar 2 are exactly equal to 1, I will have here some f tilde of 1, 1, pi 1, and pi 2 equal to 0. But 1 and 1 are just numbers, are constants. Who cares about them? This is actually some function, capital F, of pi 1 and pi 2. So going back, this is equivalent to this. This is equivalent to this. This is equivalent to this, and this is equivalent to the starting physical law f of q1, q2, q3, and q4. So at the end of the day, what we have shown? We have shown that we start with 4 independent dimension full variables, q1, q2, q3, and q4, and with the physical law which expresses a relation between q1, q2, and q3, and q4. And we showed that it was possible to find 2 independent dimensionless variables, pi 1 and pi 2, with respect to which it is possible to reformulate my original problem in terms of another problem which is equivalent to the first one, but with less variables, with just pi 1 and pi 2 variables. And actually this is the end of the story. This terms the proof of the Pi theorem. Now, next thing that I would like to show you is some other simple application to the problem of the integration. So let me revisit the integration idea. So suppose that I have some at some t equal to 0, some t equal to 0, I have some heat which is concentrated in R equal to 0. And imagine that I'm allowed to, so this heat is allowed to diffuse in a region which has a temperature equal to 0 at the beginning. What I would like to do is to find the evolution of this temperature. So I have in R equal to 0 and T equal to 0 all the heat, all the energy which is concentrated in this point here. And this is allowed to diffuse in all the space, in all the region around. At the beginning, the temperature of the region U is equal to 0. What I want to find is an expression for the temperature as a function of the distance R from the point R equal to 0 and the time T. Note that I'm calling the temperature U, okay? the dimension of the temperature is of course a temperature, and I will call the temperature theta. The dimension of the energy, let me call the dimension of the energy capital E. Okay. Now, let me assume that the quantities that can affect the temperature U are time t, the distance r from the center are equal to 0, the energy, and eventually the heat capacity C, which has the dimension of an energy over volume and over temperature. Right, thermal diffusivity K, which has the dimension of L squared times T minus 1. Okay. So let me conjecture that my physical law then is a physical law which is a relation between U, and we say T, R, E, C, K equal to 0. Now let me then write down the dimension matrix. So the matrix, again, the matrix of the powers of the single dimensions for every single variables. The matrix A that I was writing at the beginning of the proof of the Pi theorem. So just for not confusing things, let me also put here some indices to remember the quantities that are involved. So for example, time has the dimension of time. So it appears in this matrix in this way. Correct? And then R, the distance from the center, has the dimension of a length. So it appears like that.
What does it mean?
Theta is the temperature. Theta here is the dimension of temperature. So U, which is the temperature, is going to have the dimension of a temperature. So in this matrix, it's represented in this way. Right? Because again, remember, U, what's the dimension of U in terms of T, L, theta, and E? Is 0, 0, 1, 0. 0, 0, 1, 0. And the small e is the energy, so it is 0, 0, 0, 1. Now, kappa, K, which we say that's thermal diffusivity, it's written here, it's T to the minus 1, so there is a minus 1 here, L to the power 2, there is a 2 here, and then 0 and 0. And then there is still the heat capacity, which is C, which has T power of T is 0, power of L is minus 3, the power of theta is minus 1, correct, and the power of E is 1. No, there is a here. So, what is M for this system? M is the number of independent dimensionful variables. No, That's actually the number of dimensions of fundamental dimensions. It's 6. 1, 2, 3, 4, 5, and 6. This is 6. So what is the rank of this matrix? Correct. I was thinking that nobody was I was going to drink. But okay, yes, the rank is 4. So this basically means that how many independent dimensionless variables can I found from this coefficient, from these quantities? That's correct. So there would be a pi1 and pi2. I know that what I have to find is a pi1 and pi2. Now, in order to find this pi1 and pi2, well, it's always the same story. Let me write the independent pi. The independent pi is dimensionless, and the independent pi can be written as t to the alpha 1, r to the alpha 2, u to the alpha 3, e to the alpha 4, k to the alpha 5, c to the alpha 6. Now I substitute the dimension of t, r, u, e, k, and c. Allow me to jump this passage because it's trivial. So what I would have is t to the power alpha 1 minus alpha 5, L to the power alpha 2 plus 2 alpha 5 minus 3 alpha 6, theta to the power alpha 3, I hope that there is no mistake here, alpha 6, and e to the power alpha 4 plus alpha 6. Now, you remember, what's the idea now? What should I do? And well, 1 because the exponent of 1 are, so 1 corresponds to t to the power 0, L to the power 0, and theta to the power 0, e to the power 0. So the exponent of t on the left hand side and on the right hand side must be the same. So I must have alpha 1 minus alpha 5 equal to 0. Then the same for all the other exponents here and there. So what I will have is, at the end of the day, a linear system in alphas. I will write directly the solution. This is basic algebra. You must be able to do this calculation. Let me write then directly the solution. The two independent solutions are minus 1 alpha, 1, 0, 0, minus 1 alpha, 0, and 3 halves, 0, 1, minus 1, 3 halves, 1. So basically this means that to this solution will correspond a dimensionless variable pi1, which I can write as t to the power minus 1 half. So it's 1 to square root of t. R to the power 1. So I have R here. Then this is, remember, temperature, U, energy are both at the power 0. Then I have k to the power minus 1 half. So it's appeared like this way. So the first dimensionless parameter is pi1. It's r divided by the square root of t times k. And the second one comes from this expression, pi2, which is going to be u times c over e times kt to the power 3 halves. Now, as I hope that you are convinced, Pi theorem tells me that f of T, R, E, U, K, and C that would be equal to 0, that would be probably quite boring to solve, is equivalent of some f of pi 1 and pi 2 equal to 0. Now, since this is just a function of pi 1 and pi 2, this allows me to think that I'm able to solve this equation with respect to one of the two variables. So let me suppose that I'm able to solve with respect to the variable pi 2, so that I can express pi 1 as some function g of pi 2. This is basically what I would have if I solve this equation in terms of with respect to pi 2. Who is pi 1? Pi 1 is r, no, sorry, the other way around. Let me do pi 2 in terms of pi 1. Sorry, it's because in my notes, well, of course you can do whatever you want, but since in my notes I have this one, let me use this, this thing. So pi 2 is u times c divided by e k t to the power 3 over 2, and this is going to be some function g, capital G, of r divided by the square root of k times t. Then let me solve this with respect to, let me isolate the temperature, u. So I will get u equal to E over C times kt to the power minus 3 half times some function g of r over square root of k. So up to now, I didn't write any equation. There is no equation here. I'm just doing some dimensional analysis. Not writing any equation, nothing of nothing, nothing. There is no real relation until now, precise relation between all these quantities. They are just dimensional relations between the quantities. But what is interesting is that I found some expression which already contains some interesting results. For example, this tells me that the temperature U, let's try to see what happens to the temperature U in R equal to 0, in the point R equal to 0. Okay? When I am in R equal to 0, this function here becomes some function G of 0. This is a number. This is nothing else than a number. So U of 0 and t is going to be something which goes like E over C times kt to the power minus 3 halves. So without solving any equation, I can already say that the temperature in the origin in R equal to 0 scales as time to the power minus 3 halves, which is already a very nice result if you consider the fact that, again, I didn't write any precise equation for my phenomenon, but I'm only considering some dimensional, it's just a consequence of dimensional analysis that I've done of the problem. And 347, I think that I would stop here. Don't know if you have any question. Questions?
Professor, sorry. Sorry.
Say it again.
Sorry. I can't understand how do you solve this problem when you wrote t alpha 1 minus alpha 5 and plus 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 is a little no.
Here.
Yes. Yes.
Okay, when I'm here, basically what I'm doing is what I want to do is to find the powers alpha 1, alpha 2, alpha 3, and alpha 4, alpha 5, and alpha 6, which allows me to write pi, which allows me to find some dimensionless variable which depends on the dimensionful quantities that I assigned at the beginning of the problem. So the dimensionful quantities that I assigned at the beginning are time, radius, temperature, energy, K, and C. Okay? So what I want to do is to find some pi that is dimensionless and that depends on these. So what I'm doing here is just to put some fake powers, alpha 1, alpha 2, alpha 3, and alpha 4, alpha 5, and alpha 6, and then to solve a linear system to find these alphas. These solutions will correspond to the pi's which are dimensionless. Here I just wrote alpha 1 minus alpha 5 equal to 0, but then I have alpha 2 plus 2 alpha 5 minus 3 alpha 6 equal to 0, which comes from here. Then I have alpha 3 minus alpha 6 equal to 0, and alpha 4 plus alpha 6 equal to 0. Now, if I'm solving this linear system, what I found is these two independent vectors. And these two independent vectors tell me what are the combinations of alphas such that the corresponding pi are dimensionless. For example, in the first case, remember that pi is given by a combination like this. Okay? T to the alpha 1, R to the alpha 2, U to the alpha 3, E to the alpha 4, K to the alpha 5, C to the alpha 6. Now, this solution here tells me that a dimensionless combination is given by alpha 1 equal to minus 1 half. So this is minus 1 half. Alpha 2 equal to 1. Alpha 3 and alpha 4 equal to 0. Alpha 5 equal to minus 1 half. And alpha 6 equal to 0. So this would give me a first combination for a first pi, which is dimensionless. What I'm doing here is just to put this information all together. So it's t to the minus 1 half, which basically means 1 over square root of t, r to the power 1, which is here in the numerator, and then this is k to the power minus 1 half, which basically means that it's going to be under the square root in the denominator. So this tells me that the first dimensionless variable is this pi 1, which is r divided by square root of t times k. The same thing for the second one, for the second combination of alphas here.
Yes, thank you. Thank you so much.
Okay. You can find the notes in the notes tab of Teams. The notes of today are still not on Teams. Possibly are going to be on Teams on Wednesday because I do not have any scanner here in this campus, and I will have to use the scanner which is in the campus in Genova. So on Wednesday you will find the notes of today and of tomorrow. Okay.
Thank you,
If there is
Professor.
no other question? Okay, great. Then thank you very much and talk to you tomorrow. Thanks.